So hi, thanks for coming out. This is me, Ryan, and as you just heard, by day I build cloud services backends for Mozilla in a 50-50 mix of Python and Node.js. But by night I find myself grappling with something of an existential dilemma. So if you've heard of Mozilla, it's probably because we make this thing called Firefox, which is a really awesome web browser. Thank you, one person who claps. But Mozilla as an organization and as a community, its mission is a lot bigger than just making Firefox a really awesome web browser. The stated mission of Mozilla is basically to protect and promote the open web as a shared global technical resource, as a platform for individual empowerment, for innovation and for opportunity. And when we talk about the web, we're really talking about two different but interrelated things, right? On the one hand, we have the technology stack of the web, which are things like HTTP, HTML, a delightful little language named JavaScript that was invented in 10 days. We also have these kind of more squishy, nebulous, sociological, cultural features of the web as we know it today. And a really important one is its openness. Right, if you want to publish something on the web, you don't submit it to the web store and wait 6 months for Webpool to give you a rejection letter based on a technicality. Right? You just put it up on the web and people can come and get to it. Likewise, if you want to access stuff on the web, you don't need to buy a particular device, you don't need to install particular software. Pretty much everyone who's doing computing these days can get at stuff that's on the web. So it's got some really interesting characteristics as a computing platform. Some people might think the last two there are jokes, like people usually don't think of the internet as being particularly secure or trustworthy. But really, the whole job of a browser when it's interacting with the web is to go and fetch code from a site that it's probably never seen before, right, and execute it locally on your machine in a way that doesn't let them hack you, right, and also doesn't violate your privacy or your trust, like it doesn't accidentally leak your browsing history to random sites that you visit. So there's this interesting kind of mix of properties that are pretty unique to the web. The dilemma is this. I'm not really interested in any of the stuff in the column on the left, right? But I'm really super interested in all the stuff on the right. And I know a lot of people who look at the technology stack of the web and just go, oh my God, will the web please hurry up and die so that we can replace it with something better. Perhaps some of you in this room feel this way, and that's fine. The thing is that although these two things are very different, they're also very intertwined. So you can't just kind of throw one out and keep the other. And if you give up sort of the technology stack of the web, well, maybe we're giving up all of this other good stuff that we may not get back. So when I look at that picture, I think, for all its flaws, the web is worth keeping. And if we're going to keep it, we might as well try and improve it, right? And our CTO, Andreas, puts it this way, is basically anything that the web can't do or isn't faster and better at than native technologies, anytime someone would reach for a native technology, we should consider that a bug in the web. My response to that is, actually, Andreas, I did find a bug in the web. Thanks for bringing that up. I want to write in Python, right? So it was about this time last year, pycon-au last year, I started hacking on one possible fix for this problem, PyPy.js. And I want to cover three broad topics, basically what, how, and why. So the first question is what, and in a sense that's really simple, right? It's the PyPy Python interpreter compiled for the web. So ta-da! I can print, hello world or whatever and do Python-y kind of things, which is kind of cool. But I'm certainly not the first to tread this ground, and I certainly won't be the last. So probably worth a little bit more of a detailed look at exactly what is on offer here. So the first thing to note is that this is very much an experiment. I'm in a little bit better position than this dog. I know enough about what I'm doing to be dangerous. But this is not something I want to encourage you to go home and rewrite all of your production stacks in. It's just an experiment in what's possible with the technologies of the modern web. So the first thing that I focus on is PyPy.js is a really compliant Python environment. So as a simple example, we actually have big nums by default, right? And some of these other projects that try to get Python-like stuff into the web basically compile down to JavaScript's number model, which is doubles. Which is fine, like that's a perfectly valid choice, it runs fast and all this sort of stuff, but it's not Python in a very real sense. We also have lots of other fun stuff like, mutable globals that work properly. We have even funner stuff like sys.getFrame, which is one of my favorites. So basically, this is designed to look as much like a Python environment you would get natively as possible on the web. The other thing that it tries to do is be fast. Now, not necessarily like Fortran number crunching fast, although that would be pretty okay if we could achieve that. But the question is, can we make Python in the browser fast enough to take performance off the table as a consideration, where all of the other nice properties of the web and of Python kind of come into play? And it's so maybe a better word would be not slow, but we'll see how we go. I've been experimenting with this delightful little benchmark called Pystone, which ships by default with Python. I don't want to make any grand claims about the validity of this as a macro benchmark. It's a thing that you can run, and it sort of measures how fast it goes, right? So this is the native CPython on my machine. It gets about 70 to 80,000 Pystones per second. This is PyPy on the web. I'll do the same thing there. And it gets approximately half that, right? 30 to 40,000, which for a thing running inside a web browser is pretty good. Hey, half the speed of the native Python. What I've very sneakily done here, though, is primed up the JIT, and it's generated some specialized code for me at runtime. So if I run this a second time, it'll actually come in at nearly 140,000 Pystones per second, which is faster than the native CPython on my machine, which is pretty cool. It's actually really interesting to have a look at the way this develops. So I showed you that in Firefox, and it came out like so. If you ran the same experiment under Chrome, it would start off a lot slower, because Firefox has some special case handling of the kind of JavaScript you're using here. But the steady state behavior in Chrome is much faster, because Firefox has some special case handling of the JavaScript that doesn't work particularly well for what I'm doing here. And of course, if you throw a native PyPy interpreter into the mix, obviously it's going to be the fastest. But I think the gap there is not embarrassingly large for kind of an experiment in technologies on the web. And I think there's a lot of scope to close that in a lot of places. So I was sort of saying, well, we're probably approaching fast enough for our purposes doing interesting things on the web. The third thing I really want to focus on is being a proper in-browser Python environment. So this isn't just a Python console on the web that you can go and type Python commands into, right? This is a thing that's really of the web as much as it's just on the web. So on the one hand, that means having a proper JavaScript API. So it's like you can create a new PyPy VM, right? And then it gives you back these promises. All the JavaScript kids are using promises these days. So you can do a callback for when it's initialized. The JavaScript API basically gives you three pieces of functionality. You can set global variables in the interpreter. You can evaluate code to change the values of those variables, and you can read those variables back out, which is a pretty coarse API, right? The reason for that is basically, why would you want to spend your time in JavaScript when you can spend your time in Python? So this is enough to bootstrap you into a Python environment. Now go over to Python and do all your interesting stuff over there. So my in-browser Python has this cool little module called JS, which I can use to do the equivalent of what the JavaScript environment was doing. Right? And you see it gives me back a handle to a JavaScript number, because JavaScript numbers are not the same as Python numbers. They're doubles, as this kind of shows up here. But they do know how to kind of cooperate with Python numbers transparently, right? Because we have magic methods and all this sort of fun stuff. I also have access to the JavaScript global namespace, so I can do fun stuff like this. Yeah, alert is, that's the latest in modern web tech. No. I also have jQuery in the page here, because I'm using it for some of my slides. So I can do cool stuff like find this console window and change its background color to, I don't know, purple. Purple's pretty cool, right? let's get rid of that monstrosity. I can also make a little callback function like this, and I'll just print out a nice wrapper of the elements in our HTML. Not all of it, because they're huge. So then I could do find all of the slides in this presentation and call this callback function on them. And you get all the inner HTML, right? So I'm working on trying to really say, what would it look like if, all right, you've got Python, it's in the browser, and how does it get into the browser environment? So there are a lot of rough edges here, like there's garbage collection and a whole bunch of crazy stuff that's not going to work quite right. But I'm actually pretty happy with how that's come together. I was like, I think I started that about 3 weeks ago, and it kind of fell into place quite nicely. So to kind of tie all of that together,
basically what I'm trying to do here is experiment with building a fast, compliant, and in-browser Python environment. And I haven't seen a lot of other projects that kind of hit all three of those. There are projects that'll take Python and translate it into JavaScript, and they run really fast, but you kind of give up a lot of the edge cases and cool tricks that make Python Python. There are projects that put a lot of work into simulating a full Python environment in JavaScript, but they pay for it in terms of performance. So I'm hoping that we can, with some of the new technologies that are coming out both in the Python world and in the JavaScript world, maybe we can come up with something that really ticks all of these boxes. There is a but on this slide, but. This is, as I said, an experiment, and I don't want to just come out here and put on a show, this is the best thing ever, everyone needs to load this up. So there are a couple of things that are pretty rough, and a couple of things that will probably be a deal breaker for you taking this home and running it right now. But it's working enough that maybe we can start doing interesting things. The first is that sometimes it's not so fast. So I want to show you another benchmark, which may be more indicative of real-life performance. Who knows with these things? Summing up a bunch of numbers, right? That's pretty fast. We should be able to do that pretty fast. Should be able to do that pretty fast. If I put one more 0 on there, it'd give me a this script is not responding warning. But then I'd have to wait for 10 minutes for the slides to go on. What's ironic is that if I had done PyPy without its JIT, it would run faster than this example. So remember I mentioned there was a bug in Firefox that had performance problems? It turns out that this code is so, the inner loop of this is so small, and it's really dominated by infrastructure stuff. That basically all you're seeing is this huge performance degradation in this edge case of Firefox's JavaScript. So I'm fairly confident that we can get away from pathological bad behavior like this. Well, we're not there yet, so I don't want to give you any false notions. What I'd really like to see is a PyPy Speed Center with lots of more realistic benchmarks. We'll see how we go. The other thing is that it's humongous. And I mean, this is the files that you need to download to run this thing. And let me tell you, when you're measuring the size of your JavaScript files in megabytes, you're going to have a bad time on the internet. Right? A lot of this is just stuff that needs to be chipped away. There's 16,000 function definitions in there right now, almost all of which will never be called. But it's a long, slow road of figuring out how to get this down. Is that acceptable for you? Almost certainly not. Could it be acceptable to you if it was a little smaller? Maybe. And as it gets smaller, the potential applications will grow. So that's a work in progress. Oh yeah, I was going to do this. This is how long it takes to load up from my local disk when you're parsing 16,000 JavaScript functions. Which is not a lifetime, but it's not quick. So anyway, what I'm really interested in with this is the how, because it sort of came about from my interest in two independent projects, one in the JavaScript world and one in the Python world, that when you say them out loud, sound stupid, but actually work really well. So the first is PyPy. And who's familiar with PyPy? Almost every hand goes up. PyPy is a Python interpreter written in Python, hence the name. And you're like, what? How on earth could that possibly be fast? And they have two tricks to it. One is that they write it in this restricted subset of Python called RPython, which if you squint and if you exert an incredible force of will in your toolchain, you can take this restricted subset of Python and compile it down into C. And then you can compile that with GCC, and you get a native executable rather than something that runs in Python. The other trick that they have is that they built a just-in-time compiler generator. Because building just a just-in-time compiler would have been too boring, I don't know. But you have this thing written in Python, and during the process of translating it into C, this magic JIT compiler generator examines the structure of your interpreter loops and figures out how to generate a just-in-time compiler for the thing that you're compiling. So in practice, this is what the PyPy toolchain looks like, right? You start with this interpreter written in Python. You run it through RPython to get a bunch of C files. You compile those with GCC to get a native interpreter that you can then stuff your Python code into. Right? It will execute your Python code and go along and figure out, oh, actually, these pass through the code are really hot. I'll generate, at runtime, specialized native code. So in a sense, you wind up sort of running an approximation of your Python code natively. And that's why PyPy sort of manages to be so fast. which is, from where they start, is an astonishing feat of engineering. My interest in it is it's explicitly designed as a platform for hacking and experimentation. Right? So there's really nice layering and separation of concerns. You can plug bits in and out. They want to try like different dictionary implementations or a different backend and things like that. It's really, really suited for that. And kind of the speed thing is a nice little bonus. The other project that's really interesting at the moment is a thing called Emscripten. What Emscripten does is it's basically a backend for the LLVM compiler toolchain that instead of generating like, I don't know, x86 or ARM assembly, it's a compiler backend that generates JavaScript, which again is just like how could that ever possibly be a useful thing? But it turns out it can be, which says a lot about modern JavaScript. It's also like a bunch of supporting infrastructure for this stuff. So it's basically a whole simulated POSIX environment with like a file system and stubbed out process management functions that don't do anything, and get time and all of these POSIX-y functions. The guy who built it originally did it for porting games to the web. So I met him in the US, and I was like, how on earth did you have this terrifically awful, awesome, crazy idea? He's like, oh, I was writing this game in C++, and I wanted to put it on the web. Well, that's the entirety of his explanation. Like, cool. I salute you, sir. So the way it works is astonishingly simple for what it does. It's like a standard cross-compile, right? You start with some C code. You run it through this wrapper around your LLVM compiler toolchain. It spits out some JavaScript. When you give that JavaScript to a web browser, modern JavaScript engines themselves have these just-in-time compilers inside them. So it will take that JavaScript, start executing it, figure out what parts are hot, and kind of generate a native equivalent of the hot parts of your code. So you kind of eventually get to the same point you would get to with a native compiler, but going through JavaScript in the browser. The reason this can work in any kind of sensible fashion is that the guy that was building this basically discovered this tiny subset of JavaScript, which if you squint is like a little tiny virtual 32-bit CPU buried in this horrible mess of an object system of JavaScript, right? And basically the code looks like this, and there's a bunch of trickery going on in this code. So the first thing to notice is we're taking a closure. So we're making a function that creates other functions inside of itself. Inside that closure, we're taking a local reference to math.square-root. Right? In JavaScript, what this does means that reference will now immutable. There's no way any code in the whole system can make square root be some other function than math.square-root. Right? When we get down to working with variables, like we're casting them explicitly to, in this case, doubles with a little plus sign in front of them. And because of the way JavaScript works, like once you've done that cast, it now knows that the thing you're dealing with is a double. So asmjs, which I think I have the name, yeah, asmjs is like this collection of hacks and tricks that you can do to make your JavaScript be really friendly to a JIT compiler. And it turns out that modern JavaScript engines run this stuff really fast. So by omitting this kind of crazy low-level subset of JavaScript, it can actually be really efficient, which is amazing. So I had this brilliant idea. I said, let's squish the two of these together. It's going to come out beautiful. We'll start with a Python interpreter written in Python. We'll run it through this translation toolchain to get a bunch of C files. We'll compile the C files to JavaScript using Emscripten, and we'll put them in the browser, which will JIT them into native code. I will take my Python script and feed it into this native code, and it will start executing it, and it will figure out what the hot paths are, and then it will generate at runtime specialized JavaScript based on the behavior of the code it's running, which the browser will happily convert back into native code. So I've got to the same place I wanted originally, where I'm running this kind of native-ish version of my code. Be honest, whose first thought when they saw this going on was approximately, that is awful. That is a horrific collection of backwards compatibility hacks and laying violations. True. But consider this. This quote-unquote assembly code that is being generated by the JIT, when it hits the CPU, gets translated into the CPU's own internal language of microoperations. Because x86 is 30-odd years of backwards compatibility hacks on a thing designed in 1978. And the CPU will try and predict what branches it's going to take and speculatively execute them, rearrange your instructions so that it can do them in a more efficient way. So I submit to you that this is indeed an awful collection of backwards compatibility hacks, but the entire edifice of modern computing is exactly this kind of awful all the way down. So perhaps the question that you have right now is why? I think my feelings on the matter were best summed up by this Saturday morning breakfast cereal cartoon. And when people say why, they kind of expect you to go into this advocacy mode. So this guy is a science advocate, but the same applies for engineering. It's like, why is this thing important? Oh, it has lots of really practical applications and blah, blah, blah. I am unashamedly a lot more like this guy, except without the swearing. Like, why are you doing this? Because it's awesome. But seriously, this is unapologetically a playground for me, first and foremost. Like, these are some really awesome technologies that seem like they could have this fantastic synergy if you put them together in the right way. Let's see what the possibilities are. That said, I think, you know, maybe not right now, but going forward, there will be more and more potential practical applications for this. So people's first thought, obviously, is like, hey, Python in the browser, I want to do this. I want to write like script tags, text equals Python. And I just want to say you could totally do this with PyPy.js right now. Let me reiterate something I said earlier in the talk. If your users need to download and parse 15 meg of JavaScript to see like the scrolling text on your website or whatever, they're going to have a bad time. You should probably consider some of the alternative projects which sort of make a different set of trade-offs in terms of compatibility or speed, but one of the things that they both get right is they're a lot smaller. I hope to be useful for that someday, but hey, 15 meg of JavaScript is not there right now. That said, you're not always, the user's load time is not always in the hot path, right? So none of you had to sit around waiting for me to load these slides. So I went ahead, and I don't know if you noticed my little timer ticker, but anyway, I went ahead and implemented my slides logic as a script text equals Python tag. So it's totally doable, but it just takes a really long time to start up. And you know, this is using jQuery, it's using time.time and stuff. Thanks, man. That said, maybe there's more fun stuff we can do. Like, people really like things like py2exe, where you take an existing Python application, you bundle it up with all of its dependencies, and you spit out a thing that runs on Windows or Mac or whatever platform you're on. Like, maybe we could use this to build the Py2Web, right? You take an existing Python app. I'd love to try this with a game or something. Just like bundle it up, and here you go. Here it is on the web. And then stick an application manifest on that and run it on the Firefox OS device and get access to some non-zero percentage of the worldwide smartphone market. Take that Firefox OS app and run it through the Mozilla APK factory and get an Android app, a native Android app out of it, and then get, you know, a few more percent. Another interesting application someone suggested to me was like, maybe there's interesting things we can do here with the scientific community. You know, they've got the IPython Notebook and all of this awesome stuff that's kind of happening on the web. Can we plug into that and provide, like maybe we get NumPy working and we can do interesting things in a fully native web platform rather than having to depend on kind of this mix of servers and clients. So really what I want to do, oh no, I have one more point before I really want to do that. What's interesting about this approach is that you get a lot of free stuff, right? I didn't have to write a Python environment, and I didn't have to write a bunch of JavaScript optimizations. You may have noticed that I'm currently in Python 2. So if you want a Python 3 version of this, you check out the Python 3 branch of PyPy and compile it, and you have Python 3 on the web. If you want to run PHP on the web, consult a professional psychiatrist. No, if you want to run PHP on the web, you check out the PHP VM that the PyPy guys have been working on. You compile that, and you run it in the web. So I'm a huge fan of getting free stuff, and I like the possibility of lots of free stuff kind of flowing out of this. But what I really want to encourage people to do is adopt this approach of filing bugs against the web. It's like, hey, I want to do this thing on the web. Why can't I do that? You know, there are people who will take that as a serious bug. You can feel free to email me, and I'll see what I can do. I might even get it filed in bugzilla.mozilla.org. It might languish for 10 years, but you know, we'll get it on the record and see what we can do about really improving this platform. How am I going for time, by the by? 5 minutes, awesome. So I had one more question I wanted to throw in here, segueing in from that, which is who? So basically, this project has been me hacking around for a year trying to see what's possible, right? Maybe you'd like to get involved. You know, there's a huge amount of work that would be required to take this from, you know, kind of fun demo through to thing that people are actually using in the real world. So you know, if you're interested in compilers, or optimizations, or if you know some awesome tricks for reducing the size of a compiled JavaScript file by a couple of 100 times, I'm going to be hanging around for the sprints. Get in touch with me. If you feel like this is something you'd like to come along and hack on, the build environment that you need takes about 3 hours to set up. So you might want to let me know beforehand. Well, you've got to compile LLVM, you've got to compile PyPy, you've got to compile a bunch of stuff before you can even get started. Other than that, yeah, thank you very much. This has been a lot of fun for me to work on and a lot of fun to present, so I'm kind of hoping other people will be able to have fun with it too. And if you want to read more, you can go here and here. The talk materials online, and I'll be happy to take any questions. So thanks very much.